Hello, our project is the portable accessible docking system Outriggers. Our team is made of Kevin Bannock, Alex Campbell, Kyle Eichmeyer, Landon Jensen, Trevor Schwer, and Kyler Segale. Our advisor is Dr. Merriweather. The PADS is a large pontoon boat used to allow spinal cord injury patients to experience and participate in water sports such as kayaking and fishing. Currently, the PADS has issues with the back sinking in the water and listing during high winds or if the weighting of the PADS becomes uneven. The main goals of this project are to increase the boat's stability, buoyancy, adding usable deck space, easy to deploy with minimal assembly, and to be stored on the pads internally. These outriggers will provide a more stable, safe environment for the patients and their care teams while using the pads.
To ensure a safe and effective outrigger, we developed objectives based off the customer's needs and our requirements for safety and functionality. The stabilization of the vessel during weather and uneven weight distribution is the largest problem with the current pads. By adding outriggers, we wanted to reduce the roll of the pads by 25% and submersion of the rear by 30%. Through stabilization analysis, we were able to achieve this. With each patient in a powered chair accompanied by 2 therapists, deck space becomes limited during use. The customer asked us to increase the usable area by 6.5 square meters, so multiple activities can take place simultaneously. The outriggers provide 7.8 meters squared of increased deck space. The frame of the outriggers will often be occupied by multiple users. A 4,500 Newton load was used in simulation to represent the patient and the team. The outcome of the finite element analysis was a factor of safety of 3.91, satisfying our metric and customer's requirement of a robust design. The safety railing on the outrigger helps to keep all personnel on the vessel. Adhering to the Coast Guard standard for design and strength, the railing must withstand a single point load of 890 newtons and a distributed load of 730 newtons per meter on the top rail. Using finite element analysis, our design satisfied the requirements with a safety factor of 2. Kayaks and other equipment used on the pads are kept in the back where the outriggers sit when not in use. Space for this equipment must remain with the outriggers attached. A 2.84 cubic meter region is required to do this. With the outriggers stored, there is 5.92 cubic meters of usable space for equipment.
The deployment and storage function of our outriggers is shown in the top middle images. The bottom image shows how the pads and outrigger will be deployed while in the water. After working through a couple different design ideas, we decided on a fold-out outrigger design. With this design, the outriggers and deck fold into and out of the rear side doors of the pads. To deploy and retract the outriggers, 2 ceiling-mounted winches are used. The winches are used to lower the outrigger, and then the deck is held in place by a connecting link. This design accomplishes a couple of key customer needs. The outriggers are easy to deploy with minimal assembly. They store easily inside the pads with the doors closed. This feature allows for easy transportation. Also, when stored, this design retains most of the existing storage space as the pontoons are up high. Other features of this design are that this design utilizes the existing onboard power source, which keeps the new wiring simple. And finally, this design required the least modification to the existing pads.
The main areas that we were asked to improve on were the roll stability and the rear submersion of the pads, as the pads begins to rock during rough weather and the rear end tends to sink or pitch into the water during loading and unloading. In order to verify our design, we conducted an analysis to determine the improvement in these areas. First, we studied the stabilizing moment in the roll direction as shown on the left side of the stabilization analysis section. The horizontal line shows the water level for 50% submersion of the large pontoons. 50% is the industry standard for buoyancy ratings and seemed like the most reasonable place to start our analysis. We then looked at the volume submerged if the pads were to tilt about the center of gravity as shown by the tilted line, with everything below the line being submerged. We used SolidWorks to determine the volume below the waterline and calculated buoyancy using Bernoulli's equations. Lastly, we calculated the net moment about the center of mass of the pads, incorporating the buoyancy forces and the weights of the outriggers. The graph below shows the stabilizing moment with and without the outriggers. Over the first 10 degrees of roll, we calculated an average of 150% improvement in stabilizing moment about the roll axis. We conducted a similar analysis for the rear submersion by rotating the pads about the pitch axis and cut the pontoons along the length of the pads. We then calculated the net moment about the original center of mass before the addition of the outriggers, including the moments due to the weight of the outriggers and the buoyancy forces of each pontoon. The graph below shows the result of this analysis with an average of 33% improvement in buoyancy moment about the pitch axis. Based on this analysis, we have met our metric of success for rear submersion and exceeded our metric of success for stabilization about the roll axis.
Displayed in the upper right-hand corner, we have broken up our outrigger into several critical components. Number one, the threshold plate is a long stainless steel plate that's functionality is to connect the outrigger to the piano hinge. It also bridges the gap between the deck and hinge, allowing for the frame to lay flush with the existing pads. Number two, our mounting bolts are what's used to attach the outrigger to the pad's internal structure, along with the threshold plate to the outrigger. These bolts will be drilled directly into the pad's existing frame and will give us the best structural rigidity. Number three is the safety railing, which will provide a strong rigid structure to prevent passengers from falling into the water. The railings are removable and are locked into place only when the outrigger is deployed. Number four, the piano hinge allows the outrigger to be deployed and retracted with a winch as displayed in the functionality images on the left. It has a 270 degrees of rotation, which makes it possible to pull the outriggers completely inside the pads. Number four, the top links and attachment provide structural rigidity, locking our outrigger into place when it's deployed. These are easily adjustable and removable and will also be used to lock the outriggers into place when stored. Number six, the frame is the structural component of the outrigger that provides for the expanded deck space as well as the structure to mount the pontoon. Lastly, number seven, the pontoon provides the buoyancy force that stabilizes the pads under harsh weather conditions, as previously explained by Trevor.
In conclusion, through simulation and analysis, we have successfully designed the pad's outrigger system. Though we did not have the opportunity to fabricate all the necessary components, we are confident in our design and have left the Trails program with a framework to complete the outrigger at a future date. Fabrication of the system is in progress currently and is expected to be completed in time for the summer 2021 events. We determined our design met all the project goals, namely 150% of more roll stability, 33% more rear buoyancy, and 7.8 meters squared of additional deck space, all while maintaining a structural safety for all occupants. From all of us, thank you for allowing us to present. Thank you.